Hello students, I am your lecturer Shanta Mukherjee. I welcome you all for today's session on Unit 1 ARM Embedded System and ARM Processor Fundamentals. In the previous session, we discussed about three-stage pipeline in ARM 7. What are the advantages of pipeline? What are the disadvantages of pipeline and registers? In three-stage pipeline, in ARM 7, we have three stages. The stages are fetch, decode, and execute. And we studied the three-stage pipeline with an example. I took an example in the first cycle, add, second cycle, subtract, the third cycle, compare instruction. So in the first cycle, only add instruction is fetched. In the second cycle, subtraction is fetched and add instruction is decoded. And in the third cycle, compare instruction is fetched, subtract instruction is decoded, and add instruction is executed. In the third cycle, the pipeline is going to be filled. The process of filling the pipeline that I explained with the diagram. So after that, we studied what are the advantages of pipeline and disadvantages of pipeline. When the pipeline is filled, after every cycle, each instruction starts getting execution. So to do this, the circuit of the processor or the processor design becomes complex and expensive. So that we studied in the disadvantage of a pipeline. But in advantages, we studied that the execution speed increases because the process of fetching the instruction while decoding and executing the previous instruction is called as pipelining. So to do all these activities simultaneously, the processor speed definitely increases. And because of this, the throughput increases and the performance also increases. But one big disadvantages we found out in the previous session that whenever the processor executes the branch instruction, so the branch instruction will jump to some other location. So the pipeline will not be proper, or that instruction will not be going to execute because it jumps to some other location. So that becomes the pipeline hazard. So whenever the branch instruction comes, because of branch instruction, the pipeline hazard occurs. So that becomes the disadvantage of a pipeline. So those things we studied in the previous session. And we also studied about the registers. So total 37 registers we discussed. Out of 37, 17 are active registers and 20 are hidden registers. The hidden registers are called as a bank registers. They are not visible to the user. The 17 registers are visible to the user. These 17 registers are available in user mode and a system mode. So out of 17 registers, the R0 to R12, they are referred as general purpose registers. So they can hold either data or address, and remaining R13, R14 and R15, they have got the special function. So R13 is meant for stack pointer, which holds the address of the stack top, and R14 is called as a link register, which holds the address of the return instruction whenever we call the subroutine, and R15 is a program counter, which holds the address of the next instruction to be fetched. And two processor registers we studied, CPSR and SPSR. CPSR is current program status register, and SPSR is saved program status register. So out of these two, CPSR is available in user mode and system mode, and SPSR is available in remaining all other modes. So what are those modes? User mode, system mode, supervisor mode, I'm telling you. So those things we have not studied in the previous session. So today we will discuss what are the different processor modes and in which mode what are the different registers we are going to use. That we'll discuss in today's session. So the today's topics to be covered are current program status register, that bit structure we are going to study, what is each bit, the content of the current program status register. Each bit is the function of each bit we are going to study in CPSR, and what are the different processor modes. So which bits are allocated for different processor modes, that we are going to study in today's class, and which are the bank registers, and each mode have processor mode is having which bank register, that we are going to study. And after that we are going to study about the applications of our processor, and I am going to solve some multiple choice questions. Let us begin our topic with current program status register. This is the bit structure of current program status register. You can see here. So the status register starts from 0 to it ends up to 31. Why it is 31? Because the current program status register is 32-bit wide. From 0 to 7, 8 bits, they are called as control field. So there are 4 fields you can see here. First one is control field, second one is extension field, third is status field, and last is flags field. Total 32 bits are there. You would divide 32 bits into 4 parts. So 4 into 8, 32. So control field, 8 bits. Extension field, 8 bits. Status field, 8 bits. Flags field, 8 bits. Total 8 plus 8 plus 8 plus 8. So total it is 32 bits. In control field, you mark from 0 to 4, or you can write 0, 1, 2, 3, 4, 5, 6, 7. So the control field from 0 to 4, they are meant for processor mode. So in previous session, I was telling about the processor mode. So I did not explain what is processor mode. Today you will come to know what is this processor mode. M0 to M4. 0 to 4 means how many bits? 0, 1, 2, 3, 4. So total 5 bits. So the bit starts from M0 to M4. They are referred as processor mode bits. Bit 5 in the CPSR register is T bit. So it gives the thumb state. So in the beginning class I explained the ARM processor, it executes ARM instruction as well as a thumb instruction. It supports both the types of instruction. So that is decided by which instruction is going to execute. Is decided by this bit, that is bit number 5. Bit number 6, it is F, and bit number 7 is I. These two are called interrupt mask. Whenever the peripheral devices request the service of the processor, whenever they want to interrupt the processor, so with the help of these 2 bits, I can tell you whether the interrupted peripheral device is interrupt request or a fast interrupt request. There are 2 types of interrupt request. Bit number 7 is IRQ, interrupt request, and bit number 6 is F. F stands for fast interrupt request. By seeing the status of these 2 bits, we can tell whether the peripheral devices request the interrupt request or the fast interrupt request. Extension bit, bit number 8 to 8, 9, 10, 11, 12, 13, 14, 15. So bit number 8 to 15 is extension field. These bits are reserved for the future use. They are not used in this present current program status register of ARM7. Next, bit 16. So 16 to you count 16, 17, 18, 19, 20, 21, 22, 23. 16 to 23, 8 bits, they are reserved for status. They are called as status field, and it is reserved for the future use. Extension field and status field are reserved for future use. So where we get ended here, status field 23. After 23, the bit number is 24. So 24 you start, 24, 25, 26, 27, 28, 29, 30, 31. 24 to 31 are reserved for the flags. So we can use the flag field and the control field in ARM7. Control field completely from 0 to 7 you can use. Flag field Out of 8, again we are going to use only 4 bits. They are 28, 29, 30 and 31. 31 is N, 30 is Z, 29 is C, 28 is V. N stands for negative flag, Z stands for zero flag, C stands for carry flag and V stands for overflow flag. So these flags are called as condition flags. So here you can, below I have written here function. So they indicate what the each bit does, which function that is decided by these bits. And above I am showing as a fields here, what are the different 4 fields, and below that there is bit here. Each line indicates the bit number. So 0 to 31. So this is the way how to write the bit structure of current program status register. It is also referred as CPSR. Now we'll study one by one each bit. What is 0 to 4 indicates? What is bit number 5? Bit number 6, bit number 7, 28, 29, 30, 31, one after the other. Let us begin from the flag field only, bit number 24 to 31. So they contain 4 conditional flags. So the first one is I am taking negative. So negative flag. Negative flag is bit number 31. It is used to determine whether the result is signed number or a unsigned number. So after the arithmetic operation, whether the result is positive or negative, so that is given by this bit number 31, negative flag. If n flag is 1, the result is signed and it is negative number. If n is the most significant bit in every 31st bit is the most significant bit, always the most significant bit tells whether the number is positive or negative. If n is 1, the result is negative. If n is 0, the result is positive. So you can, by seeing the content of the n bit, we can decide whether the number is positive or a negative. So next bit is 0, 30. Remember 30 is 0, 20 is carry and 29 is carry and 28 is overflow. So Z flag, it is bit number 30. It is used to determine whether the result is 0 or non-zero. After addition or subtraction, so whether we get the output value is 0 or non-zero. So that is given by the 0 flag. If Z is equal to 1, result is 0. If Z is equal to 0, the result is non-zero. Non-zero means output contains ones and zeros or all ones or zeros and ones. But result 0 means all the bits will be 0. So if the result is 0, then Z becomes 1. If the result is non-zero, the Z becomes 0. 29-bit carry flag. It is used to determine whether the carry has occurred after the addition operation or subtraction operation. So this is applicable for borrow while doing the subtraction. So there is no borrow flag in CPSR. So only the carry flag is there. For addition, it is used to determine whether the carry has occurred or not. But in subtraction operation, the same carry bit is applicable for borrow also. So there is no specific flag like borrow. The same carry flag indicates whether the borrow has occurred or not in the subtraction. So if C is equal to 1, carry has occurred after the addition operation. If C is equal to 0, carry has not occurred after the addition. So if C is equal to 1, carry occurs. If C is equal to 0, carry does not occur. Bit number 28 is overflow flag. It is used to determine whether the signed overflow has occurred or not, whether signed result has exceeded. For example, if you are adding 2 numbers and 4-bit numbers, and the result should be 4-bit number. If it is exceeding 4, if the result is exceeding 4-bit number, then definitely overflow occurs. So it is used to determine whether the signed overflow has occurred or not. The result has exceeded, that is the result has exceeded. If V is equal to 1, signed overflow occurred. If V is equal to 0, signed overflow has not occurred. For signed operations, if you are doing the operation on signed numbers, then the overflow flag comes into the picture. If V is equal to 1, sign overflow occurs, and if V is equal to 0, sign overflow has not occurred. And remaining from 16 to 23 bits, they are status field, they are reserved for future use. Bit number 8 to 15, it is referred as extension field, it is also reserved for future use. And bit number 0 to 7, it is called as control field, it contains interrupt mask, thumb state and a processor mode. Now we'll study what are those bits in control field. Interrupt masks are used to disable interrupt request selectively. I told that whenever the peripheral devices request the processor for the service, they can interrupt the processor on the interrupt line. So the processor can disable it. If it does not want to give the service to that peripheral device, it can disable the interrupt. Then how it is disabled? So with the help of I and F bits in a CPSR. So because it is disabling the interrupt request, these two bits are called as a interrupt mask bits. So they are referred as interrupt mask bits. There are two interrupt request levels. So they are interrupt request IRQ and fast interrupt request FIQ. So the peripheral devices can interrupt the processor on these two levels, interrupt request and a fast interrupt request. Accordingly, there are two interrupt mask bits. They are denoted as I and F. So the bits, bit number 7 and bit number 6, they are called as interrupt mask bits. And bit number 7 is I stands for interrupt request. Bit number 6 is F stands for fast interrupt request. So how it disables and enables the interrupts? If I is equal to 1, disables the interrupt request IRQ interrupts. If I is equal to 0, enables the IRQ interrupts. If F is equal to 1, disables the FRQ interrupts. If F is equal to 0, enables the FRQ interrupts. And T is bit number 5. It reflects the states of the processor. So whether the ARM is executing the thumb instruction or the processor ARM instruction, it is decided by the T state. So if T is equal to 1, processor is in thumb state. So T stands for thumb. Definitely it must be 1. So if T is equal to 1, processor is in thumb state. If T is equal to 0, processor is in ARM state. So these are the processor bits from 0 to 4. So they are used to select the current processor mode. So we have total 7 processor modes. So with the help of these 4 bits, we can select the different processor modes. What are those different processor modes? The first one is user mode. FIQ stands for fast interrupt request mode. IRQ, interrupt request mode. Supervisor mode, abort mode, undefined mode, system mode. Total 7 processor modes are available in a ARM. So they are given in the bit number 0 to 4. So the 0 to 4 bit, you can see here 1 followed by 4 zeros. 1000 indicates the user mode. If you enter 1000 in the 0 to 4th bit, it goes to the user mode. If you write 10001, it goes to the fast interrupt request mode. 10010, it goes to the interrupt request mode. 10011, supervisor mode. 10111, abort mode. 11011, undefined mode. All ones, system mode. So you need to remember these bit values to tell you about the different processor mode. So if I ask you what is the bit value for undefined mode, you should tell it as 11011. So there is simple trick to remember these bit numbers. So see here, first all MSB are 1. See, last value MSB bit is 1 in every board. So no need to remember this. You just write bit number 5, 1, 1, 1, 1, 1, 1 in all the modes. Then you start writing 000 indicates 0 here, 0001, 1, 0010, 2. So leave the last bit, consider only the 4-bit. The value is 0, 1, 2, 3. After 3, 7. 7. After 7, 11. After 11, F. 1, 1, 1, 1, F. So in this pattern, you can remember the bit values. So try to write this diagram. It is very helpful for your examination. The same thing I have shown here. The processor can operate in 7 different modes. The modes are used to select the current processor mode. CPSR, how many processor modes the CPSR has? So it has 7 processor mode. How to select the 7 processor mode, using which bits? So from 0 to 4. So what are the different processor modes you have? You start from user mode, FIQ, IRQ, supervisor, abort mode, undefined mode, and a system mode. You need to remember in the same order. Then only you can write the bit values here. If you write wrong bit values, the processor mode will be changed. So remember the bit values in the order and modes in the order only. So this processor mode determines the active registers and access rights to CPSR. How many active registers are present in each processor mode, and how to access the CPSR content, that is decided by this processor mode. Each processor mode is either privileged mode and or non-privileged mode. So out of 7 modes, which modes are can be used as a privileged mode and non-privileged mode? Then what is privileged mode and a non-privileged mode? Privileged mode, it allows full read and write access to CPSR. Complete CPSR 0 to 31. So we will have write access to read as well as a write. Full read and write access is there on CPSR. So if it is there, then that mode is called as a privileged mode. Remember, you will have privilege to full read and write access to CPSR. Such mode is called as a privileged mode. Non-privileged mode, it only allows read access to control field. Control field 0 to 7. And flag field starts from 24 to 31, 24, 25, 26, 27, 28, 29, 30, 31. So 24 to 31, it is flag field. And out of 24 to 31, only 4 conditional flags are there: 31, 30, 29, 28. So you will have read and write access only to the conditional flag, only read access in the control field. Such mode is called as a non-privileged mode. So don't be in confusion. Privileged mode means full read and write access. Non-privileged means there is no read and write access. In that way, it is not there. So for some field, read and write access is there. For some field, only read access is there. So you remember, in control field, you will have only read access, and in conditional flag, you have both read and write access for of the CPSR. So total, there are 7 processor mode. Out of 7, 6 are privileged mode. Privileged means you will have write access, you will have full read and write access on a CPSR. So 6 are privileged mode and only 1 non-privileged mode. So it is easy to remember. The non-privileged mode is user mode. User mode is non-privileged mode, and remaining 6 are privileged modes. The privileged mode can change the mode by writing to CPSR. So this privileged mode can change the mode by writing to CPSR, because privileged mode have both read and write access. So remember, there are 7 processor mode. Out of 7 processor mode, only 1 non-privileged mode. The non-privileged mode is user mode. Remaining all modes are privileged mode. User mode is non-privileged mode. So what is each mode indicates? So in this, First I am taking abort mode. The processor enters the abort mode when there is failed attempt to access the memory. So whenever you are going to access a wrong memory, suppose you are reserving a memory from 20002 to 20020. So you need to access these memory location only, because you have declared these memory location to store some values. If you are accessing the data from some other memory location like 3000, definitely, so it enters the abort mode. So the processor enters the abort mode when there is failed attempt to access the memory. You are declaring the memory location 2000 to 20020, but you are going to access the different memory location 3000, then the system processor enters into the abort mode and it gives the message as you are trying to attempt to access the wrong memory. So this is abort mode. Interrupt request mode. This corresponds to interrupt request level. So the peripheral devices can request the interrupt. So if I becomes 1, so the interrupt is disabled. If I is equal to 0, the interrupt coming on that line is enabled. In the same way, fast interrupt request mode, this corresponds to fast interrupt request level. So if the high performance peripheral devices wants to get the service, they can interrupt on this line, fast interrupt request mode. Then supervisor mode, the processor goes into the supervisor mode after reset. Whenever you reset the processor, immediately the processor goes into the supervisor mode. So this point is very important. You may get in the multiple choice questions. So after the reset, the processor goes into which mode? So it goes into the supervisor mode. Operating system, once after reset, the operating system operates in this mode, because the operating system it is loaded and it goes into the supervisor mode. Undefined mode, it is used when the processor encounters an instruction that is undefined or not supported. So whenever you are executing a wrong instruction, for example, if you are executing add instruction, it is a correct instruction. The mnemonic is ADD. So instead of ADD, if you write ADB, it's a wrong instruction. So it is used when the processor encounters an instruction that is undefined. ADB is not defined and it is not supported by the processor. In such case, the processor goes into the undefined mode. System mode. It is a special version of the user mode that allows full read and write access to the CPSR. So system mode allows full read and write access to the CPSR. User mode, it is used for programs and applications. So for programs and applications, the user mode is used, and it is only the non-privileged mode. So what is non-privileged mode? So in non-privileged mode, you will have read access to control field and read and write access to conditional flags. This I have given the table in order to remember the different modes very easily. So the processor mode determines which registers are active and access rights to CPSR. Each processor mode is either privileged or non-privileged is given in this table. So abort mode, it is the abbreviation for abort mode is ABT. Fast interrupt request mode, FIQ. Interrupt request mode, IRQ. Supervisor, SVC. System, SYS, the first 3 letters, and undefined, the first 3 letters, UND, and user, USR. These are the abbreviations for the 7 processor modes. So which are privileged here? I told user is only the non-privileged mode, remaining all are privileged mode. So answer is yes, 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 yes here, and for user it is no. And I told you to remember the bit numbers from 0 to 4. All MSB are 1. Then here from the user mode, from the beginning, in the previous slide I have shown from the user mode. So here they are showing from abort mode. So you remember the previous mode, it is easy to remember. So this completes the different processor modes. Now I will discuss about the banked register. So which registers are used in which processor mode, that we can see it in this diagram. So banked means they are hidden register which are not visible for the user. See, user and system mode together have all these registers shown. Next comes fast interrupt request mode, interrupt request mode, supervisor mode, undefined mode, abort mode. Count it 1, 2, 3, 4, 5. And here there are two modes, user mode and a system mode, total 7 modes. So you have to write the diagram in this order only. First, FIQ should come. Next, IRQ should come. Then supervisor, undefined, abort should be the last diagram. Abort is last. User and system is first. FRQ, FIQ, IRQ. And then you remember supervisor and a undefined mode. And user and system mode, don't shade the diagram here. For remaining all modes, you shade the diagram. Here it is shaded: fast interrupt request mode, supervisor, undefined and abort. They are all given in a shaded form because the shaded register indicates they are not visible to the user. The unshaded registers, they are visible to the user. Then how many total registers are there? Will let us count now. In user and system mode, R0 to R15, how many registers are over? 15, 16 register, and one CPSR 17. There are total 17 active registers in a user mode and a system mode. Then in fast interrupt request mode, the same registers are used from R8 to R14. See, R8, R9, R4, R10, 11, 12, 13, 14. Same registers are used with the suffix FIQ. So why the suffix is used? Because each mode will have the same user and system mode registers are used in order to differentiate the processor mode suffix is used. Since it is fast interrupt request mode, the abbreviation is FIQ. So R8 underscore FIQ, R9 underscore FIQ, like that R14 underscore FIQ. So in this way we have to write. And in interrupt request mode, only the two registers are used, R13 and R14. So the suffix is underscore IRQ. Supervisor mode, suffix is underscore SVC. Undefined suffix is UNDEF. And abort mode, the suffix is ABT. In this way, you have to write it. Then in FIQ, fast interrupt request mode, the register from R8 to R14 are hidden here. They are hidden register, but fast interrupt request mode can use the general purpose register R0 to R7 in the same manner how the user and system mode are using. Only R8 to R14 are hidden registers. Then interrupt request mode, only two registers are hidden, R13 and R14. Remaining from R12 to R0, it can be used as general purpose registers in interrupt request mode. In supervisor mode, again two registers are used, R13 and R14. They are hidden register. Remaining R12 to R0, they can be used as general purpose registers. In undefined mode, R13 and R14, they are hidden registers. Remaining all register R12 to R0, they can be used as general purpose registers. In abort mode, same way, R13 and R14 are a hidden register and they are called as a banked register. Remaining R12 to R0 can be used as general purpose registers. So all these registers are called as a banked registers. So you can see here in user mode and system mode, only CPSR is shown. And there is one more status, saved program status register, that is SPSR. SPSR, you can see it only the bank register. So SPSR, what is the suffix of FIQ, fast interrupt request? FIQ, SPSR FIQ. If it is in interrupt mode, SPSR IRQ. If it is in supervisor mode, SPSR SVC. If it is in undefined mode, SPSR UNDEF. If it is in abort mode, SPSR ABT. So SPSR, saved program status register, this is available in the banked register, which we cannot see it in the user mode and the system mode. But CPSR is not there in all the bank register. R0 to R7, so These registers are completely the general purpose register for all the boards, and R8 to R14, so they are used in fast interrupt request mode, and R0 to R12 they can be used as general purpose registers in all other four modes: interrupt, supervisor, undefined, and abort mode. Now total registers in user mode and system mode are 17. You count it, they are 17. In fast interrupt request mode, the number of registers used are 8. Here there are 7. One more is plus 1. So 8 register. Interrupt request mode, 3 register. 2 are banked register and 1 bank register for SPSR 3. Supervisor has got 3. Undefined has got 3. Abort has got 3. Total how many register? 17 plus 8, 25, plus 3, 28, 31, plus 3, 34, plus 3, 37. Total number of registers in ARM processor are 37. Out of 37, 17 are active register, remaining 20 are banked register. So you count the banked register, number of banked register starts from 8 here. 8 plus 3, 11, 11 plus 3, 14, 14 plus 3, 17, 17 plus 3, 20. Total 20 bank register and 17 active registers in user mode and system mode. So this above figure shows all 37 registers in a register file. Out of those, 20 registers are hidden from the program at different times, and these are called as banked registers. Banked registers of particular mode are denoted by underline character postfixed to the mode mnemonic or underscore mode. Example, R13 abort, R8 FIQ, etc. So the SPSR is not visible in user mode and system mode. You can see here. In this diagram, up to CPSR, the user can see it. SPSR is not visible. So SPSR is not visible in user mode and system mode. User mode is non-privileged mode. What is non-privileged mode? It only allows read access to control field in CPSR. System mode is privilege. All other modes are privileged mode except user mode. System mode is privileged mode. It allows read and write access to control field in CPSR. Then user mode and system mode do not have banked registers. So they do not, you see the diagram, you do not have banked register in user mode and system mode. Only the active registers you can see here. So user mode and system mode do not have banked register. Banked register corresponds to 16 registers, R0 to R14 and one more SPSR. And there is no banked register for R15. See here, banked register from R8 to R14 it is starting. R15 has no banked register because R15 is for a program counter. Program counter always holds the address of the next instruction to be fetched. It cannot be used as a banked register. So R15 is not banked register. Banked register starts from R8 to R14. Depends on the modes, the number changes here. So this is about the banked register, very important topic. So you should be able to draw that diagram, banked register diagram, and you should know how many registers are there in user mode and system mode, and how many banked register in FIQ, how many banked register in IRQ, how many in supervisor, how many in undefined, how many in abort mode. So you should remember, and you should be able to tell what are the registers used in each processor mode. So that we studied in the banked register topic. The last topic is applications of ARM processor. So networking applications, like they are used in home gateways, digital subscriber line DSL model modems. We can use the ARM processor for high speed internet communication. It is used DSL modems, and 802.11 wireless communication also we can use the ARM processor. So all we know that the application of ARM is mobile phone. So mobile phones and personal digital assistant ARM processor is used. Automatic car, consumer devices like washing machine, microwave ovens, So here they are used, and mass storage devices like hard drives, inkjet printers, and cost sensitive and high volume applications like digital cameras. So these are very important applications of the ARM processor. Along with these applications, I have given some more general applications, video games, robotic applications, mobile computers, MP3 player, DVD player, TV remote, set-top box, iPod, Xerox machine. In all these, we can use the ARM processor. So at least the above slide, this is very important for the examination. You remember all the application. So these are extra applications. So try to remember all these applications. Now we'll solve the multiple choice question based on the structure of CPSR and the processor modes and banked registers. Consider a 4-bit ALU which does the 4-bit arithmetic. When the following 4-bit numbers are added, what is the value of NZCV? So two numbers are given. The numbers are 1101 plus 1011. You add these two numbers and tell me the result. Here I have shown you the result also. So 1101 plus 1011. Add these two. 1 plus 1 is 0 with carry 1. So 1 plus carry 1 is 0 with carry 1. 1 plus carry 1 is 0 with carry 1. 1 plus carry 1 is 1 with carry 1. So your result is only 100. So now we'll discuss what are the different flags are going to set. So one result is 100. Is it zero result or non-zero result? It is non-zero result because the result has got 1 here. If all the result bits are 0, then 0 flag is set to 1. Otherwise, 0 flag is 0. So the 0 flag becomes 0 because the result is non-zero. The most significant bit is 1. Result is 100. In this result, the most significant bit is 1. If the most significant bit is 1, the result is negative. So n becomes 1. And whether the carry is occurred, it is shown in the red bit. Yes, the carry is occurred. C becomes 1. Whether overflow has occurred, no, the result is not exceeded. It is 4-bit result 100, and we are doing the unsigned number addition here, and the result is 100. The overflow does not occur, so V becomes 0. So N is 1, Z is 0, C is 1, V is 0. Result is 1010. Search the option. The option D is the right answer. 1010. So you write down this value in your notebook and find out the result and try to analyze the flag fields here. So then you check the option. One of the option will be right. That is option D. Which type of non-privileged processor mode is entered due to rising of high priority interrupt? So the peripheral devices can interrupt the processor on IRQ line and a FIQ. So FIQ is fast interrupt request. For higher priority interrupt, it is taken. So they have asked high priority interrupt. The answer must be FIQ. So user mode, it is not an interrupt request only. We cannot give the interrupt request mode. Supervisor mode, no. So we can give the answer as fast interrupt request mode. Which mode allows full read and write access to CPSR? Privileged or non-privileged? So privileged mode gives full read and write access to CPSR. Non-privileged mode, it will not give full read and write access to CPSR. Answer is option B. Abort mode generally enters when an attempt access memory fails. Whenever you try to access the wrong memory, then abort mode processor enters into the abort mode. So the option is answer is option A. Which bit reflects the state of the processor, whether the processor is in thumb state or arm state? Which bit is representing in the CPSR? It is thumb state. So if t is equal to 1, the processor enters into the thumb state. If t is equal to 0, the processor enters into the arm state. So the answer is option B. Thank you all. We will meet very soon in the next session.